Hi, everybody. Welcome to Net 208 session. My name is Tom Adamski. I'm a specialist solution architect focusing on networking. I'm joined today by Theo Salvo, who is a specialist solution architect, but in containers. And with our container and networking powers combined, we have a session for you on Amazon Elastic Kubernetes Service and the networking patterns it supports. We'll start off with a bit of a Network Foundations recap. So summary of the base building block of the AWS networking. If you're already familiar with those base building blocks, it's going to be much easier for you to translate those components into the Kubernetes world. But if you're completely new to networking, that's going to be a quick introduction to get you on-ramped along with everybody else. And then we'll move on to cluster connectivity from a management perspective. I'll talk about the base building block, the pods, and how they communicate. And then I'll hand off to Theo to talk about more advanced concepts like exposing services, service discovery, and service meshes. We're going to spend most of the time on explaining the architectures and how things are plugged together. We won't be including a lot of how you deploy things. That's something you can look up. There will be a few examples, but just expect this to be focused primarily on the networking architectures. So to start off with the foundations recap, here is an example region, US East 1, that's North Virginia. I'm showing 2 availability zones, but it actually has 6. They wouldn't fit into the drawing. And this is your physical infrastructure on which you will be deploying your logical components. And the primary logical component is your virtual private cloud. That is your private environment. Think about it as your virtual private data center. You decide what goes inside of that environment. You decide what that environment communicates with. And the first thing you need to do is decide on the IP address blocks that you allocate to this environment. And it supports both IPv4 address space as well as IPv6 address space. From an IPv4 perspective, you would typically use a private IP address block, like the example here, 10.0.0/16. From an IPv6 perspective, AWS can allocate you with a publicly routable or globally routable address block, or you can bring in your own address space into the VPC as well. Once you decide on the CIDR ranges for your VPC, you can start subdividing them further into subnets. And subnets would be deployed inside a particular availability zone. So a VPC spans the whole region, subnets live in particular availability zones, and they use an IP address block that's a subset of the original CIDR range. Once you have your subnets defined, you can start deploying resources into those subnets. Throughout the session, we'll be using Elastic Compute Cloud Instance as an example. That's a virtual machine that lives inside AWS. But this could be any other components. This could be a managed database service. This could be a load balance service. And those instances would actually be using Elastic Network Interfaces to communicate with everything around them. Think about those as just logical NICs, network interfaces. And they do support dual stack, so they can use IPv4 as well as IPv6 address space and use the appropriate IP address depending on what they're connecting to. A single instance can have one or multiple Elastic Network Interfaces, and a single network interface can have one or multiple IP addresses. Now, this VPC right now is completely isolated, but if we want to connect it, say, to the internet, we would need to do a few things. First of all, we'd deploy an internet gateway, and that's a managed gateway. AWS supports multiple different types of gateways depending on where are you connecting to. So if you're connecting to the internet, you need an internet gateway. You would also need to allocate an IPv4 public IP address. If you're using an Elastic IP address, it just means it's a public IP address that can move around. But the private IP address before it leaves through the internet gateway has to be translated to this Elastic IP address. From an IPv6 point of view, you're already using a globally routable IP address, so you don't need to do the nothing. And the final step is to set up your routing. So you need to configure a route table that you can associate with any subnets you want to allow those subnets to be able to go out through the internet gateway when they're communicating with the internet. And at this point, the instance in the green subnet can talk to the internet, but also the internet can initiate connections to that instance. What about the 2 instances at the bottom? Maybe we want to have a different behavior where we don't want anything from the internet to be able to route to those instances, but we want them to be able to initiate connections outbound, maybe to download a software update from the internet. For that, for IPv4, we need to deploy another type of gateway. In this case, a NAT gateway. NAT stands for Network Address Translation. And the NAT gateway will be translating the private IP address of the instance to its own IP address. And then when the traffic leaves through the NAT gateway, translate it again to elastic IP address that can communicate on the internet. And the NAT gateway allows for traffic to go out, but if you try to connect to the NAT gateway from the outside, from the internet, the traffic will be dropped. And for availability, with NAT gateways, you want to deploy one in each availability zone, and then configure the route tables to ensure that the traffic goes through accordingly. For IPv6, we already have a globally routable IP address. So to achieve the same behavior as the NAT gateway, kind of like a one-way door where our instance can communicate out, but nothing on the outside can initiate connections to our instance, we can use the egress-only internet gateway. And then when we configure the route tables, we can see that now we have a default route on the subnet at the bottom, pointing through a NAT gateway over IPv4, and over IPv6, we would use egress-only internet gateway. Now, we have a naming convention for these different types of subnets. So if a subnet has direct internet connectivity to and from the internet, it's called a public subnet. If a subnet doesn't have a direct route to the internet, we call it a private subnet. And if you're actually exposing services to the outside world, so maybe you're running a web application, you would present them to the outside world through something like a load balancer. So in this example, I'm using a network load balancer. It's one of our Elastic Load Balancer family components. And then that load balancer lives in the public subnet, so all the connections go to the load balancer before they get to the instance. So if we now follow the life of a packet, say our instance wants to initiate connection to the outside world over IPv4, download a patch, it will send traffic to the NAT gateway, and then the NAT gateway will translate it to its own IP before sending it out through the internet gateway and getting translated again to a public IP. If we're presenting a service, connections from the outside land on our load balancer, and that load balancer then forwards traffic to the private instances. From an IPv6 point of view, for initiating connections, we would use egress-only internet gateway, and we would have a very similar behavior that we have with a NAT gateway, kind of one-way door. Connections can initiate from the inside, but they cannot initiate from the outside. If we want to present an IPv6 service, we would do it again through the load balancer. The load balancer will have a v6 IP address, and it will forward the traffic to our backends over, in this case, IPv4. So this is a quick summary of the basics of your VPC networking. If you want to dive deeper and find out more about the foundations, there's a Net 201 session that should be available on demand when you're watching this video. Now, when we're moving to containers, we're actually using the same building blocks. We still have an EC2 instance. We still have an Elastic Network Interface. But if we were to run an application directly on an EC2 instance, there's going to be a little bit of overhead. So if we have an instance, a virtual machine per application, we would need our application, the libraries that it requires, but also the operating system. So every single virtual machine will have a Linux or Windows or some kind of operating system. So that's not super efficient if all we need is just a simple application. So with containers, we're making the compute unit a lot smaller. We now have the applications and the necessary libraries as a single unit of compute, and we don't actually require the guest operating system. We just need to have a runtime environment that will host our container. In this example, it's Containerd, but you might be familiar with others like Docker. And the other benefit of running containers is that it allows for much easier mobility, right? So I can create an application on my home machine, on my laptop, make it a container, a self-sufficient container, and then that can be passed on to production and run on a completely different environment. So the benefit of mobility and the benefit of better compute utilization. If we're moving into Kubernetes world, we're actually not talking anymore about single containers. We have the unit of compute here is the pod, and a pod could be one container or it could be multiple containers. So for example, it could be a container that's is a web application, and another container in the same pod that's only responsible for pulling logs from that web application and sending it somewhere, and maybe another container that's responsible for handling connections as a proxy. All those containers within the same pod are sharing the same networking constructs. So throughout the session, we will be talking about the pod as the primary unit of compute, and we'll talk about how that pod communicates with everything around it. Now, if you're building a Kubernetes environment, you can do it yourself, right? You can deploy all the worker nodes, because that's the naming convention for the instances that host your pods, and then deploy your pods on top. So that is your data plane. That is your data plane environment where your application lives. All the connections would be connecting to, all the client connections would be connecting to your data plane. And then to orchestrate that environment, because it would be really hard to actually run thousands of containers or worker nodes yourself, you would have a control plane. So control plane nodes and some database. That's something you can deploy yourself in AWS, put it in different availability zones, manage it yourself. And then that would be used both for controlling the data plane and scheduling the pods and deciding what gets deployed where. But at the same time, this would be the control plane would be what you're connecting to with Kubernetes command line, kubectl or kubectl, whatever you prefer, to apply the changes that you require. So the top bit is the control plane, bottom bit is our data plane. If we translate this into AWS managed service, Amazon Elastic Kubernetes service, AWS will take care of the control plane. So you no longer have to deploy anything. That's all a managed service. And then you can make a decision on how much of the data plane you want AWS to manage for you. You either have the option to do self-managed nodes, where you manage the worker nodes and you attach them to your cluster. You can have EKS orchestrate the deployment of your worker nodes and automatically attach them to the cluster, but then you still have to perform some of the management functions yourself. And then finally, with AWS Fargate, that's where you just give us a pod directly and you don't have to manage any of the underlying components. In the session today, we'll spend most of the time talking about connectivity for self-managed node and EKS managed node groups. So with the data plane and the management plane, there are some management connections that are required to establish. Firstly, from the worker nodes themselves when they talk to the control plane, and then from your Kubernetes CLI when you're making changes to the environment. So let's look at some of the examples of how you can configure that connectivity from a management perspective. So here we have your VPC where you would deploy your worker nodes in the worker subnets. There would be a separate VPC managed by AWS where the EKS control plane would live. That's not made visible to the customer, so you don't have to worry about that VPC. That's something that we manage for you. And each one of the control planes would have an EKS-owned ENI that lands in your VPC. It's good practice to put that into a separate subnet. Now, if we establish and we set up the management and cluster endpoint access as public, what this means that if worker nodes need to communicate with the control plane, they need to go out through the internet gateway and then communicate with the control plane through its own internet gateway. So if I'm inside of the VPC and I do a DNS lookup of the cluster API endpoint, which is kind of used by the control plane, I would get returned a public IP address. So I need to have a path to get to that public IP address through the internet gateway and then hit the control plane. There's also some load balancers in here for distributing the traffic that I'm not including. The important bit is that with public access, you have to go out through the internet gateway. And then if you're managing your control plane from kubectl and you do look up the API endpoint somewhere outside on the internet, you will get the public IP address as well, and you would apply your management changes through the public path. You also have the option to enable public and private access. In that scenario, if you are inside of your VPC and you do a DNS lookup for the cluster API, you would actually get returned a private IP address that is the EKS-owned ENI. So those management connections initiated by the worker nodes would go to that IP address completely privately. You don't have to go out through the internet gateway. From a management point of view, outside, if you're sending, again, kubectl commands to your cluster, and you resolve the cluster API endpoints, you still get a public IP address, so you still use a public path. And the final option is to configure private-only access. So in that scenario, nothing changes for your VPC. If you do look up the API cluster endpoint, you get a private IP address, so you can still connect to that. But now if you're outside, say on-premise or maybe even working from home, and you look up the external API name, that DNS name will also return a private IP address of the EKS own ENI. And without you having an access to that ENI, that IP address would be useless. So you need to create a path from your management, from wherever you run your management commands, to the VPC that hosts the EKS own ENI. You can do that through setting up things like AWS site-to-site VPN or client VPN, or setting up Direct Connect. And then you have a private path to that IP address. So that is the management plane. Let's move on to the data plane and how pods communicate within your environment. And I'll focus here on IPv4 connectivity. If you're watching this right now, you might want to look up any changes that has happened since we're talking about IPv4, but that's going to be our focus today. So with Kubernetes, there's some recommendations that Kubernetes provides on how the pods should be communicating. So some guidance like every pod should have its own IP address, the fact that containers sharing a single pod are really sharing the same networking space like we discussed earlier, and the fact that pods communicating to other pods shouldn't have to use NATing. So all of these requirements can be achieved in a modular fashion. So you can install a container network interface plugin. This is effectively a pod itself, or a daemon set of pods that controls how that networking is done. And because it's modular, you can decide on different providers to provide the functionality, the network functionality that you need. And Amazon has an Amazon-provided CNI that specifically focuses on pod and Kubernetes connectivity within a VPC. So in our example here, we have a VPC with a worker subnet, we have a worker node, and it would be running the Amazon CNI plugin. And the way we would allocate IP address to the pods is we would have a primary network interface with a particular IP address. We would have some secondary IP addresses on that ENI, and then as pods get provisioned on the worker nodes, they would get IP addresses allocated from that secondary range. And that's something that the CNI plugin takes care of. So it will make sure that every time there's a request for a new pod, an appropriate IP address gets assigned. And once we run out of secondary IP addresses, every primary ENI will have a limit of how many secondary IP addresses it can have, depending on the type of the EC2 instance. The Amazon CNI would then allocate another network interface with another set of secondary IP addresses that would then get allocated to the additional pods. And because this is a modular concept, there are other CNI providers that you can use. And some of them can completely replace Amazon CNI if you want. Some of them work in tandem with Amazon CNI. So for example, Calico has an option to be added on top of Amazon CNI to give you extra security functionality. So if we look at how pod-to-pod communication looks in this scenario, let's add an additional worker node, maybe in another subnet. It will also have a primary ENI with some secondary IP addresses and a bunch of pods. And then if we have two pods here that need to communicate, they would just use their allocated IP addresses and communicate natively within the VPC. So the pod on the right would actually see the real source IP address of the pod on the left connecting to it. So that's exactly following the Kubernetes requirements and recommendations. Now with Amazon CNI, you also have a number of different options that you can change depending on what you require the CNI to do. And we'll focus here today on 4 primary options. There's more. We just didn't have time to cover all of them, but these are the ones that I think are the most relevant right now. And each one is configured through a command line. So that's one option, how you configure these, and you're changing environment variables to true or false, depending on if you want to enable or disable a particular option. So starting off with source NATing. Source NATing allows you to enable NATing or network address translation on the worker node. And you'll notice here that the command we're using actually says external SNAT equals false. So it's a little bit counterintuitive, because if you say external SNAT is false, that means you want the worker node to do the NATing. So source NATing enabled means external SNAT false. So what does it mean? So if the worker node, say it is in a public subnet, and we have pods that want to communicate with something on the internet, we already know we need an internet gateway and an elastic public IP address that will be allocated to the primary ENI, primary IP address of the worker node. So now if we have a pod trying to communicate with the internet, it would use its own IP address,
but before it leaves the worker node, it would get translated. Its source IP would get translated to the worker node primary IP 10.0.0.20, and that would be the IP address that initiates a connection to the internet, hits the internet gateway, and gets translated again to the Elastic IP address. So the NATing at that point is only applied if the traffic is leaving the VPC. If you're communicating still within the cluster, within the same VPC, this source NATing would not be applied. Now, if we want to disable NAT, we actually have to say there is an external SNAT. So we change the external SNAT option to true. And the external SNAT option for IPv4, we already know what that is. That is a NAT gateway that has its own ENI and has an Elastic IP address. Now, a worker node could be in a completely private subnet. And as the pods need to initiate connections to the outside world, they would send traffic directly to the NAT gateway with its own IP address, and the NAT gateway would translate that IP address to its own IP address and then send it out through the internet gateway when we would translate it to a public IP address. Okay. The other option I want to touch on are secondary IP addresses for pods and how that impacts how many pods we can deploy on a particular instance type. So I mentioned earlier that every instance type has a limit of how many secondary IP addresses it can have. It also has a limit of how many additional network interfaces it can have. So if we look at the M5 large EC2 instance and we look up the documentation, it can have maximum 3 network interfaces with 10 IP addresses. So that means each interface will have a primary IP address and 9 secondary IP addresses. And we already know that pods will get IP addresses from the secondary IP addresses. So here, 3 times 9 is 27. There's also 2 additional pods that will be running on the worker node that don't use secondary IP addresses. So with that calculation, the total number of pods we can run is 29. So this is, at this stage, with this type of configuration, the number of IP addresses could become a limiting factor for how many pods you can have running on a particular instance. Something that we launched a few months ago across the whole VPC is the ability to assign a prefix to an EC2 Elastic Network interface instead of a secondary IP address. So with a prefix assignment, you're assigning blocks of IP addresses. For IPv4, it's a /28 that equals 16 IP addresses. For IPv6, that equals /80, which equals 280 trillion IP addresses. So how does it help us with a port density? So if we go back to our M5 large instance, now for every single secondary IP address, instead of using a secondary IP address, we can use a delegation. And each delegation equals 16 IP addresses. So now we have a lot more IP addresses that are available for pods. And this actually means that the maximum IP addresses is no longer equal to maximum pods. With maximum IP addresses here, if we look at IPv4, we would have 432 IP addresses and trillions of IPv6. With maximum number of pods, it's now 110. And this number is derived from other recommended best practices. So we're looking at CPU, memory, other constraints, not just the IP addresses. And if we look at an example of how this looks like on our worker node, we would have the primary NI, but this time instead of secondary IP addresses, we have prefix delegations /28s, and then those would be used to allocate IP addresses to the pods. And then if we were to run out of them on a particular network interface, the Amazon CNI will take care of adding additional interfaces and then using those with delegations to attach additional IP addresses. So benefits here, we're actually getting higher port density. As I mentioned, IP addresses are no longer the limiting factor for pods. And also on the back end, there's less API calls when we have to request additional IP addresses and additional ENIs. The third option I want to talk about is related to setting up security groups for your pod environments. By default, when you set up your worker nodes and your pods, a security group would be wrapped around the network interface that's attached to your worker node. And all of the pods that are using secondary IP addresses from that network interface would share the same security group as your across all of the pods. So if you have a web pod and if you have an FTP-based pod, all of them, you'd have to allow traffic on the same security group to access all of them. And that's something that you might not want. Maybe you want to be more granular. One option here is to use additional configurations within your Kubernetes environment, maybe network security policies. Or the other option we have is to use branching and trunking. So these are concepts that were launched specifically for Elastic Kubernetes Service or our Elastic Container Service. They're not natively available at EC2 today. And the concept here is having a trunk interface and then branch interfaces that are associated with the trunk interface. If you're familiar with networking, this is similar to your sub-interface configuration on your devices. So if we translate that to our configuration setup, we have here a worker node and pods configured on top. Now, with a trunk interface, we can use the branch interfaces that are mapped to that trunk interface to be allocated directly to the pods. And now each pod, because it has its own Elastic Network Interface, can have its own security group where you can be very specific about what permissions you're configuring here. There are some considerations here. So this is only available in a specific type of instances and a specific cluster version. So make sure you read up on the details when you're deploying this. The final option I want to talk about is custom networking. And this specifically helps with situations where you don't really have enough IPv4 addresses to assign to your environments, right? Your containers, your pods are very IP hungry. They do get an IP address from the VPC. So many customers I meet don't have enough IP space to actually allocate to all of the clusters. In the example here, we changed the VPC CIDR range to a much smaller block, a /24. That translates to around 251 IP addresses across the whole VPC. So that is not a lot if we want to run thousands of pods. So custom networking allows us to help here. So one thing we will do is enable custom networking. So set that to true. And the other thing we need to do is add a secondary CIDR range to our VPC. In the example here, I'm using 164/16. So that gives us 65,000 IP addresses. And that will be only relevant to the VPC that we're deploying this into. The next thing we need to do is create subnets from the primary 10.0.0 range, as well as from the secondary 164 range. And then as we deploy our worker nodes, the primary interface of each worker node would go to the primary CIDR. And then secondary, tertiary, and all the additional network interfaces would go into the secondary CIDR subnets. And then pods would only use the secondary CIDR IP addresses, only 164. So it means we now have a lot more IP addresses that we can use for pods. And if you want to read up more about the 164 range, that's a range that is used very similar to the RFC 1919. So it's kind of treated like a private range. Now, what if we need to communicate from that VPC with the outside world, right? If our pods need to get out of that VPC and communicate with other things. We can combine that configuration with the concepts we're already familiar with, like SourceNAT, and connect our components using a transit gateway. And let's explain that with an example. So we have a VPC here on the left. It's a client VPC. It's using 10.0.0 and 164. We have another VPC where we host a service on the right-hand side. It's using a unique primary range, 10.0.1. And the secondary range is still the same, 164. Again, it will be only relevant to this VPC. We have a service presented through the Elastic Load Balancer that we will be consuming, and the Elastic Load Balancer is deployed into the unique primary range. The pods, however, can still be in the secondary range, 164. We connect that environment using an AWS Transit Gateway, and you can think about a Transit Gateway as a logical distributed router managed by AWS that allows you to create hub and spoke topologies and connect different VPCs together. And a Transit Gateway would have a route table that you can configure, and in that route table, you would configure routes only to the primary ranges of each VPC. You wouldn't really configure a route to the 164 because it's used in every single VPC, so it's overlapping. The Transit Gateway wouldn't know how to get to it. But it's not necessary because we wouldn't be using it to get out of the VPC. So how do we hide that 164 range? If a pod tries to communicate with the service on the right, the service is already in the routable range, 10.0.0.1, but the pod is using 164. But as it's leaving the worker node, source address translation could translate that IP address to the worker node IP address in the 10.0.0 range that is routable and can use the transit gateway to get to the load balancer on the right-hand side. The load balancer then terminates the connection, hides the IP address, and forwards it to the actual pods that can, again, run in the 164 IP address space. And this works for other environments as well. It doesn't have to be a container environment. You can actually have an EC2 instance on the right-hand side, or it could even be an on-premise network, your corporate data center connected to the transit gateway using Direct Connector VPN. With this mechanism, you now can have thousands of IP addresses available for your pods and not waste any of the primary IP space that might be constrained in your network. Okay, and with that, I'm going to hand off to Theo to dive into exposing applications in the Kubernetes world.
Thank you, Tom. Now let's talk a little bit more about how we can take some of this information we just learned about the networking and EKS, and let's actually look at how we expose those services to the rest of the ecosystem. For one, we need to make sure that we're running the AWS Load Balancer controller. This is a Kubernetes project that's been built and designed to bridge the gap between Kubernetes and AWS networking components. For example, if you create a Kubernetes service, we want that to map to a networking load balancer. If you create an ingress, we want it to map to an application load balancer. These are different frames and different ways that we can create this, and we're going to keep going through some of these resources. But when we go to configure a network load balancer, what we're going to do is we're simply going to create our Kubernetes service as normal, and we're going to specify the type as load balancer. That will automatically create the network load balancer as part of the AWS resource. We can also add some additional fields to configure the network load balancer by creating annotations on top of the service. Whenever we configure a network load balancer, there's two different target types that we can talk about, since the network load balancer supports both instance and IP mode. When we create a network load balancer through a Kubernetes service using instance mode, it will create the network load balancer and the target group, and the Kubernetes cluster will actually configure the node ports on the instances and the primary ENI to actually represent that service on an ephemeral port and to pass that through to the pods themselves. This behaves just like it would for any other application, and that traffic does pass through the kube proxy running on each worker node. However, if we change that to an IP mode, we're able to use that pod's IP address inside the VPC and actually point the target group directly to that IP address in the port that's running. This skips kube proxy and allows the traffic to go directly through for your application. Similarly, when we want to build application load balancers, instead of using a service resource, we're going to use an ingress resource. Ingress resources in Kubernetes are designed to allow for multiple different routes distinctly to be provided, which is a similar capability that the application load balancer provides. And so in this case, we're going to map a Kubernetes ingress to an AWS application load balancer. We're going to create the same type of rule. We're going to create an ingress. We're going to specify, in addition to everything else, the rules of how we're going to listen for it. So if we're looking at the rules in this case, if we receive traffic bound for echoserver.example.com, we're going to send it to our echo server service on port 80. The way that we define which ingress to use varies depending on which version we're using. Pre 1.19 Kubernetes and EKS, it was by adding an annotation that said this is the ingress class that we want to use, and then specifying an actual ingress class for the ALB. Once we're at 1.19 and above, is now part of the actual spec to specify the ingress class name. And so we're able to say this is the ingress class we're going to use and have an ingress class that is specifically mapped to the ALB controller that we have. While most of this is details that are specific to Kubernetes, it's at least important to have an idea of what this looks like, because as we look at it, it then has to then translate to what we do on the actual network itself. And again, just like with the network load balancer, we're able to add annotations to change some of the behavior or to specify which groups our services actually belong to as part of configuring them. So when we look at our application load balancer, again, our controller is running and we're going to configure our application load balancer as part of the ingress, which defines the listener and by default at least one target group. as we scale and we add more rules that are mapped to different Kubernetes services, we can also have separate target groups and separate rules that gets created as part of them. This allows to have that same ingress flow that we're used to in Kubernetes, but also mapping that to an application load balancer that has very specific rules about how that traffic goes from A to B. If you want to specify which one of those traffic goes to which part of the rule, there's a special annotation that you're going to add called the group name. The group name helps to identify which piece belongs to, or which service belongs to which ingress rule and to which target group. Now, of course, in case you are already using an existing application or network load balancer and you don't want to transition away from that, it is possible to map Kubernetes services simply to a target group using what's known as a target group binding. This is a special resource that was created specific for the controller that allows for your Kubernetes service to map to a target group only without going through and creating either a network or an application load balancer. And that target group is able to be used as necessary and configured inside the AWS console. What we're after here is choice. We don't want to change the way that you're currently using your workflow, and this gives you the flexibility to make sure and use the way that you want to. Next up, let's take a look at service discovery. When we talk about service discovery, the first thing to always consider is how we do DNS resolution, as DNS has been used for service discovery for many years. Well, when we think about how we're incorporating the DNS of the Kubernetes cluster with the DNS of the VPC, it's important to remember that anytime our pod needs to make a DNS call, it's first going to go to the core DNS, which is a service that's running inside the Kubernetes cluster. That core DNS server, if it cannot resolve it, will send it out to the Route 53 resolver, which is typically the .2 inside of that VPC. And of course, if that Route 53 resolver cannot find anything, then it'll of course send it to any upstream DNS that you have. Now, when we think about that, let's actually consider what are some of the domain names that exist and where does the authority exist for each one of those names. So you may be familiar with on Route 53 resolver, the default names are ec2.internal or compute.internal, depending on which region you belong to. Core DNS and Kubernetes also creates new authorities that exist, service.cluster.local and pod.cluster.local. And the authority for those remain with core DNS. Anytime that you create a new service or add a new pod inside of Kubernetes, that service name .namespace name will automatically register inside core DNS. If anything does not fit the service.cluster.local or pod.cluster.local, then it is forwarded out to the Route 53 resolver. Well, this presents an interesting problem, especially as we try to configure multiple clusters for DNS. Because of the fact that core DNS uses service.cluster.local, if we have two separate clusters with two separate groups of worker nodes, that means that we have two separate instances of core DNS running. And therefore, I can't have a pod on the left side be able to reference a pod on the right side using the pod.cluster.local domain, because the left core DNS will always think that it should be inside of there and return as unable to resolve. It won't go to upstream DNS either to do so. This is true for whenever we're spread out across multiple clusters across multiple VPCs, or if we have within the same VPC multiple clusters. Because of the fact that they're each running their own copy of core DNS, this traffic will not pass through and DNS will be unable to resolve. Well, there's a few ways that we can fix this, and one of the ways is starting is using AWS Cloud Map. AWS Cloud Map operates as a service registry, and the equivalence here is that a Cloud Map namespace is mostly equivalent to a DNS domain. So we're able to create a new DNS authority domain like services.company.internal, and we're able to use that across as many Kubernetes clusters as we need to by integrating that with Cloud Map. So each Kubernetes cluster will connect to Cloud Map using external DNS, which is a Kubernetes SIGs project, which actually allows for the DNS records in core DNS to be exposed to external DNS servers. This solution does work so that if we want to have multiple Cloud Map namespaces, we could create multiple different entries for that. And it works with all the different namespaces that exist inside Kubernetes as well by using across multiple different clusters. And because this is using bare DNS at the backbone, this also means that we're able to export or import those other records using Route 53 Resolver, meaning the CloudMap namespace can also be exposed not only to both clusters, but to on-premise or other connections that you may have into that particular VPC. When it comes to actually doing discovery with CloudMap, there are two options. The most common is DNS, which is what most of your applications are using today. With CloudMap, you're able to do A, Quad A, or IPv6 A records, or service records or SRV records, and you'll get 8 healthy records in an answer. However, CloudMap also supports an API-based discovery where you're able to specify certain attributes and get over 100 records in the answer, optimally querying on whether or not you want the health status or not. An important designation here is that if you're going to use the Discover Instances API, you are baking that into your application or into some mechanism that is able to do that API call for you. By default, if you're using a standardized framework package inside your application, it's going to try to use DNS unless you specify a custom resolver. But when we start thinking about this, the availability of having this new construct for a DNS authority allows us to create a multi-cluster DNS. So let's just say, for example, that I have workload A on the left, workload B on the right, and I've created the services.company.internal as part of AWS CloudMap. I'm now able to extend the DNS, and I can now create a pathway where workload A can talk to workload B by referencing it as workload B.services.company.internal. Core DNS says I do not know about this, which passes it up to the Route 53, which is interfaced with CloudMap and will therefore return the pod's IP address. Note that this level of service discovery does not change anything about the network behavior, and in order for these two services to talk, I still have to connect the VPCs together. To make things easier inside the Kubernetes world, there's also a project that we're working on called the MCS Controller, which stands for Multi-Cluster Service API. This is not only an API, but a controller that we've implemented using that standardized API, which adds services as part of CloudMap. This uses a new constructs that exist. For one, if you are using endpoint slices, then there will be a new record called a cluster set, which is the reference to all of the different endpoint slices that can exist. So we can actually take our services from one cluster and we can export them out of one cluster and import them into another cluster as a way of having our references. Again, this doesn't change the network path, so you still have to have that network boundary. This is merely about being able to define the resources that we're going to connect to from each Kubernetes cluster. Now that we've talked a little about service discovery, let's actually take a look a little bit further at what service mesh does for us here. If we go back to our network load balancer and we look at how we're spinning up network load balancers, if I have 2 services that are running as Kubernetes services, I could have specified a network load balancer and I will have 2 network load balancers that represents each one. Well, if I have 4 clients on the left and they need to talk to both services, they will need to talk to both network load balancers, and each one of them will be responsible for passing that traffic on to the various worker nodes and worker pods that exist for that particular application. Similarly, if I want to use an application load balancer, I could have 2 different ingress routes which end up as the listener rules inside of the application load balancer, and my clients end up connecting to a single point, but I'm able to differentiate that traffic to the 2 basic target groups that exist behind it. Now, both of these patterns are valid and we still see use for them. The problem we've seen with this is when this starts scaling out to tens or hundreds or thousands of applications and being able to maintain this connectivity and how all these applications talk to each other. And so one of the ways that we're actually able to work with and help that is by creating a service mesh architecture. So for service meshes, we establish a baseline that all of the clients and all the application worker pods exist within the same mesh, and they're able to directly reach out to each other to talk to each other as necessary. While this looks like it is more complex in form of the traffic pattern, the simplicity of this with service mesh, and represented by that purple dot on the screen, is the idea of having a proxy on top of each one of the worker pods, and therefore being able to use that as the intelligence layer to say this is how you connect to service A or service B, depending on how you want to bridge that. So let's take some of the properties of service mesh. For one, service mesh uses what's known as a distributed proxy. Now, working in networking for many years, proxy is not always one of the most favorite terms in the world, especially because of what it involved for network traffic. In order to make a proxy effective in the past, we had to centralize all of that network traffic to a single location. Same was true when we're using application load balancers today. All that traffic is centralized. Instead, I want you to think about this proxy as a distributed proxy. We have the central intelligence of what we want to do as a declarative state, but we're giving each copy of a proxy a copy of the configuration so that it understands how to behave. And that's where we're inserting our intelligence in order to affect the overall behavior of the application. So if I point your attention to the right of the screen, you see that the traffic comes in through the primary ENI. Instead of going to your application container, it's instead going to go to the proxy container first. And that proxy container is going to do its magic and is going to push that through to the application container. Similarly, on an outward path or a response path, the app container is going to send that first to the proxy container, who will then send that over to the primary ENI and back out through the rest of the port. This means that for every pod that we create and we have one app container, we're also going to have one proxy container running as a sidecar. And we're going to dynamically configure each one of those proxies using our service mesh. Because of the way that we've built certain controllers, and we'll talk about this in a second, instead of having to specify that this proxy is going to be added, or in the case of maybe you have some of your workloads are running on service mesh inside the cluster and some are not, we've made it capable to where you're able to inject that pod, the proxy sidecar, into the pod without changing your original spec. We read the original spec that came from that pod declaration, and we add in the necessary pieces to make a service mesh work. This means that you're able to take that same spec and say this runs on service mesh or doesn't run on service mesh, but that detail doesn't have to be discovered by the developer themselves. You're able to simply say, I now want this to run on a service mesh, declare it, and as an operator, push it onto a service mesh. The trick here is when we think about the pod and how that networking traffic is working, remember that two containers in a same pod share the same network namespace. And this is done down at an OS level, but they're able to communicate with each other using localhost and exposed ports. So what we are doing to make this work is we actually have certain ports that we are listening on for inward and outward traffic on our proxy. And we're actually redirecting the ENI. Instead of sending to the app container on the app port, send that to the new port on the proxy. And the proxy pushes that to the app port using localhost. Same happens in reverse. Everything coming out of the app container is pushed to a different port, and then that is eventually sent out through the ENI on whatever port it was originally intended for. What's nice about the idea of a service mesh, especially as we look towards networkers, is this doesn't change anything that you do today. Because all this is being handled inside the worker node and inside the pod, it means that the network still behaves. You still need network paths between two members of a service mesh. You still need service discovery to happen between members of a service mesh. But we can still apply security groups, firewall rules, NACLs, and all the other network security tools that were at our disposal before, even after using a service mesh. It's a fun way of saying that service mesh is great, and to a networker, you don't have to worry about it. So let's take a look at our service mesh, and again, as we think about how we're spreading this out and how we actually include the network into that scenario, let's say that we've now spread out our application to where our clients exist in one VPC and our worker nodes and our applications exist in a separate one. We're still able to have this service mesh to where these are able to talk to each other as long as we've provided that network configuration between them. In this example, we've done a transit gateway to peer the VPCs, and therefore we have that valid network path. The proxies will get the service discovery information from CloudMap or DNS, and will get that intelligence baked into that sidecar container So if client 1 needs to talk to app 2, he will create that pathway automatically, connect directly to that app 2 pod, and then complete that round trip time as necessary. The key here is we're doing this all without that load balancer. And while the load balancers are very efficient, they still add a network hop. One of the key advantages of Service Mesh is the traffic is going direct from source to destination without adding an additional network hop. Yes, you do have a little bit of latency because you are running it through not one, but 2 proxies, one at the source and one at the destination. But because all that is handled within the same process namespace and within the same network namespace, we can actually achieve things like encryption in transit without having to make any changes to the actual code itself. Thank you very much for your time today. Have a great day.